to True Projects. In this video, we are going to explain about the project entitled as Hybrid Quantum Classical Framework for Urban Traffic State Classification. So before getting into the video, let me give you the brief description about the project. The project combines classical machine learning and quantum computing techniques to accurately analyze complex traffic data. In this framework, classical models extract meaningful features from high dimensional traffic information, while quantum classifiers handle the final decision making. This hybrid approach improves scalability and learning capability compared to purely quantum models and shows stronger potential for efficient traffic congestion prediction in intelligent transport systems. Coming to the abstract states that urban traffic state classification is essential for intelligent transportation systems as it helps predict congestion early and supports efficient route management. Traditional traffic prediction methods struggle with high dimensional and time dependent traffic data, leading to inaccurate results. To overcome these limitations, a hybrid quantum machine learning approach called the multilayer perceptron variational quantum classifiers is introduced, where an MLP extract features and a VQC performs classification. Experimental results shows that this hybrid model significantly outperforms standalone quantum models and demonstrate good scalability for complex traffic data. Coming to the existing system uses traditional machine learning and statistical algorithms to predict traffic conditions. While these methods work well for simple and low dimensional data sets, they fail to effectively model complex temporal patterns found in real world traffic data. Pure quantum models like variational quantum classifiers have been explored but currently offer limited performance due to hardware and algorithmic constraints. Coming to the proposed system or base paper work, the proposed system employs a hybrid MLP VQC model that combines classical and quantum learning techniques. An MLP is used to extract meaningful features from traffic data, which are then classified using a variational quantum classifiers. This approach improves classification accuracy compared to standalone quantum models and shows better scalability with increasing data complexity, particularly when using the efficient SU2 quantum and stays. Coming to dataset, a smart traffic monitoring dataset from Kaggle contains real-time traffic data collected at 1 minute intervals using smart sensors. It includes traffic parameters such as vehicle count, speed, flow, and time steps, making it suitable for traffic state classification and congestion prediction tasks. The dataset is provided in CSV format and is easy to pre-process for machine learning applications. Coming to the novelty or extension or enhancement or improvement. As an extension, entanglement based quantum layers can be integrated into a hybrid MVQC model. Entanglement enables stronger feature representation and parallel computation, allowing the model to capture deeper correlations in traffic data. This enhancement has the potential to improve classification accuracy and strengthen the effectiveness of quantum assisted traffic prediction systems. Along with this, as an extension, the Flask framework is used to develop a user friendly interface that allows users to provide input data for prediction. The inputs are pre processed and passed to the trained model based on the data set. The predicted results are then displayed through a web interface, making the system easy to access and use. Coming to the workflow, first we have environmental setup and initialization. The workflow starts with initializing the Python environment by importing all required libraries for data handling, machine learning, visualization, and quantum computing. Warnings are suppressed to keep output clean. Key libraries including NumPy, Pandas, Scikit-learn for classical preprocessing, and Qiskit for implementing quantum circuits and the variational quantum classifiers. Next, we have time parsing and feature engineering. A custom time parsing function is implemented to extract meaningful numerical features such as hours and minutes for timestamp values in the traffic data. The step transforms raw temporal information into machine readable inputs suitable for both classical and quantum learning models. Next, dataset loading. The vehicle detection system dataset is loaded from a CSV file. This dataset contains traffic flow information collected from sensors deployed along 107 major urban roads. Initial inspection of the dataset is performed to understand feature structure and traffic class labels. Next, EDA process. Exploratory analysis is carried out to study the distribution of traffic states. Visualization techniques such as bar plots are used to identify class imbalance and overall traffic patterns, which helps in selecting appropriate modeling strategies. Next, data pre-processing. The dataset undergoes pre-processing steps including handling missing values, encoding categorical attributes, feature normalization, and dataset splitting into training and testing sets. This ensures the data is in a suitable format for training both classical and quantum models. Next, classical MLP model training. A multi-layer perceptron classifier is trained using the pre-processed traffic dataset. This model serves as a baseline for performance comparison and learns complex pattern for high dimensional traffic data using classical deep learning techniques. Next, feature extraction using MLP. After training, the MLP is used as a feature extractor by capturing intermediate layer outputs. This extracted feature represents high level abstractions of the traffic data and reduces dimensionality before feeding the data into quantum classifiers. Next, we have variational quantum classifier implementation. A standalone variational quantum classifier is implemented using quantum feature maps, parameterized quantum circuits, and classical optimizers such as Cobiol. This model evaluates the perform of purely quantum learning on the traffic data set. Next, we have hybrid MVQC model construction. The proposed hybrid multilayer perceptron variational quantum classifiers model is constructed by combining MLP based feature extraction with quantum based classification. The efficient SU2 and stays is used to design the quantum circuits due to its superior performance on small and medium data sets. Next, model training on small and medium data set. The hybrid MVQC model is trained and tested separately on small and medium subsets of the dataset. Experimental results shows that the medium dataset provides higher classification accuracy due to better data diversity and representation. Next, performance evaluation. All implemented models are evaluated using standard classification metrics such as accuracy, precision, recall, and F score. This evaluation enables a fair comparison between classical MLP, standalone VQC, and the proposed hybrid MVQC models. Next, extension using entanglement based quantum layers. As an extension, entangle based quantum layers are incorporated into the MVQC circuit. Entanglement enhances quantum parallelism and correlation learning, allowing the model to capture deeper relationships within traffic data and potentially improve classification accuracy. And next, we have comparative analysis and final results. The final workflow stage involves comparing the performance of all models using tables and graphs. The results demonstrate that while classical MLP achieves the highest accuracy, the hybrid MVQC consistently outperforms standalone quantum models and shows better scalability for complex high dimensional traffic dataset. Coming to the front end of the system is developed using the Flask framework, providing a simple and interactive user interface. It includes user registration and login functionality supported by an SQLite database for secure authentication. Users can input traffic related data through the interface, which is pre processed and passed to the trained model for prediction. The final prediction results are then displayed to the user through the front end. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consisting of operating systems, Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consisting of application framework Python 3.10.9, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front-end are HTML, CSS, JavaScript and Bootstrap 4. To execute the project first, we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. Model file. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. Notebook.ipynb file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Coming to the execution of the project, firstly, you need to copy the path from the code folder of the file explorer. Then, open command prompt. Use the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in the command prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it into any web browser. I prefer Chrome. The home page of the project should now be displayed in the browser. This is a front end built using Flask framework. In this page, we have home button and sign up button. Firstly, click on sign up button so that new user sign up form will be opened where you need to enter the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Once again, you need to reconfirm your password. Then click on sign up so that all the given details are stored in signup.db and the login.html will be opened where you need to access the application by username and password. Click on login. The prediction page has been displayed. In this page, we have prediction button, graphs button, notebook button, and sign out button. Firstly, click on prediction button so that the traffic data input form will be opened where we need to enter the traffic parameters and predict the traffic state. So let us enter the values. Vehicle count value will be 100. Average speed will be 21.2. Vehicle type will be 50 ambulance, 69 fire extinguisher and 54 truck. Traffic density is 65. Time step will be 17 is to 59 is to 00. Then click on predict traffic state. The input is pre-processed and the output is predicted as moderate. The traffic state prediction is moderate. We have the recommendations, safety directions like vehicle safety, driver safety, and road safety. Here we have new prediction button and view analytics button. Click on new prediction button so that the form will be opened and again we can test by giving the other input values. The vehicle count will be 51. Average speed is 43.1. Vehicle type will be 24 cars, 97 fire extinguishers. Traffic density is 47. Time trap will be 16 is to 54 is to 00. Now click on predict traffic state. The input is pre-processed and the output is predicted as free flow. The traffic state prediction is free flow. We also have the recommendations and safety directions like vehicle safety, driver safety, and road safety. Now again click on new prediction so that the form will be opened, and let us check by giving the other inputs. The vehicle count is 182, average speed is 48.3, vehicle type is 94 vans and 13 ambulance, traffic density is 76, and time trap will be 16 is to 55 is to 00. Now click on predict traffic state. The input is pre-processed and the output is predicted as congested. The traffic state prediction is congested. We have the recommendations and safety directions like vehicle safety, driver safety, and road safety, conjunction safety. And then click on graphs so that the graphical representations of the project will be opened. First, we have dataset traffic flow classes distribution graph. The graph illustrates the distribution of traffic conditions in the dataset, showing that moderate traffic has the highest number of samples, followed by congested, while free flow has the lowest count. This indicates a clear class imbalance which can influence model training and evaluation. Next, we have traffic volume dynamics by traffic flow graph. The graph shows how traffic volume density varies over time for different traffic conditions. Moderate traffic consistently has the highest volume, followed by congested, while free flow maintains the lowest volume levels. This illustrates clear temporal differences in traffic behavior across flow states. And next, we have confusion matrix graph. The confusion matrix shows that the classical MLP model correctly classifies most traffic states where with very high accuracy for congested and moderate classes. Only a small number of misclassification occurs mainly between moderate and free flow, indicating strong overall model performance. And next we have accuracy comparison graph. The graph compares the classification accuracy of different models used for traffic state prediction. The classical MLP achieves the highest accuracy while the proposed hybrid MQVC improves significantly over baseline quantum models. And the entanglement based extension further enhances the hybrid model performance. And next, we have precision comparison graph. The bar chart compares the precision of three algorithms. The existing classical MLP achieves the highest precision at 96.384%, followed by the extension MQVC with entangled at 94.400%, while the proposed hybrid quantum MQVC has the lowest precision of 85.455%. Next, we have recall comparison graph. The bar chart compares the recall values of three algorithms. The existing classical MLP achieves the highest recall, followed by the extension MQVC plus entanglement. The proposed hybrid quantum MQVC shows slightly lower recall. This indicates that the classical MLP performs best in terms of recall for this dataset. And next we have F-score comparison graph. The bar graph compares the F-score performance of three algorithms. The existing classical MLP achieves the highest F-score, followed by the extension MQVC plus entanglement, while the proposed hybrid quantum MQVC has the lowest score, indicating the classical model currently outperforms the quantum approach. And then click on sign out. So finally, the hybrid quantum classical framework for urban traffic state classification successfully combined classical machine learning with quantum techniques to improve feature representation and classification accuracy. The results demonstrate its potential for real-time traffic monitoring and intelligent transport systems. This study highlights the feasibility of near-term quantum computing in practical urban traffic applications and lays the groundwork for future enhancement and scalability. This is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.